second video, what I'd like to show you here is an example that is found at the bottom of page 273 in your textbook. And it is showing you how to find the center of mass of a long rod that has a total length L and a total mass M. And so you might sort of intuitively know where the center of mass of that rod is. And there's a rod in the x direction. And the reason we're considering this as our center of mass example is because it's a one-dimensional case. So we're going to integrate with respect to x from 0 to L, and it's a pretty simple case of finding the center of mass using our formula for center of mass. And intuitively, you probably know that the center of mass is going to be at the center of that bar, and so we'll find that. Okay, now the thing to know about center of mass, or any center of mass calculation, is that you need to know how the mass is distributed. And so we have this term called density, which is mass per unit volume, but in the case of a linear mass density, one-dimensional mass density, I'm going to use something called the linear mass density, which is mass per unit of length. Okay, so mass per unit of length in kilograms per meter is known as the linear mass density. And so when I use my center of mass formula where I want a little piece of mass, I'm going to have to write that mass as the mass density times the length. All right? So in other words, mass is equal to the mass density times length. And in my case, I'm going to want a little piece of the mass, one little section of the mass. Here's a little section right here, one little piece of the mass of that rod. And so I'm going to write that as the linear mass density times dx, a little bit of thickness. The little dx is like right here, dx. All right? And so here we go. My formula says the x, center of mass, is equal to 1 over big capital M times the integral, in this case from 0 to L, of what? Of x times dm. And we know, in this case, a little piece of mass along that one-dimensional bar, the mass is going to be the linear mass density times the width. And so I can substitute that in. So this is equal to 1 over big capital M times the integral from 0 to L of lambda times x times dx, okay, where lambda and dx are really the dm, okay, that's where that comes from. And so I can bring that lambda out front, so lambda divided by m times the integral of x dx. And now that's starting to look doable. Let me get rid of this example here and move everything down. So, and if you copy this into your notebook, that'll be a good thing for you to do. So you can clean it up a little bit. So the x center of mass, the center of mass of my long rod of length L, mass m, is going to be lambda divided by m times, now I have to integrate that thing, and I know that the integral of x is 1/2 x squared, and I'm going to go from 0 all the way up to L. So this is lambda divided by m, and this is going to be 1/2 of L squared minus 1/2 of 0 squared, and that piece goes away. And so finally, in the end, I'm almost there, I end up with lambda. Now, what was lambda again? Lambda was m over L. M over L. There's my lambda divided by the big mass times 1/2 L squared. And I just need to simplify that. So here I've got a mass divided by a mass. I have a 2 out here, so it's going to be L squared over 2L, which gives me L divided by 2. And that's exactly what we thought. We kind of thought that in the beginning we would expect the center of mass of that long, thin rod to be right around the middle of the rod. And that's exactly what we find. So in AP Physics C, sometimes you have to show where you're getting your values. You can't just say half L. You have to show how that works. All right? So hopefully that made sense. All right, I'll see you in the next video.